Hello, and thank you for joining our What You Need to Know about the TG-51 Addendum webinar with Dr. Larry DeWerd and Autumn Walter. We will start with Dr. DeWerd to discuss the addendum, and then we'll hear from Autumn as she discusses the methodology for stability of chambers. Now, I'll hand it over to Dr. Larry DeWerd.
Also listed the paper from the addendum, all the authors, and where you could find the paper. So if you want to go further into it, certainly encourage you to look that up. So the reference, basically the background of TG-51 alone is obviously they talked about reference chambers and KQ values, and you have to be very careful when you're doing this kind of thing, when you're doing small fields especially. So 51, usually you know this, and I'm just kind of reviewing. I'm going to talk mostly about the addendum, but you do a 10 centimeter deep, 10 by 10 field in a phantom that's at least 30 by 30 by 30. Most phantoms are larger than that, so you don't have to worry about that, but this, of course, affects small fields. There's a lot of things like the gamma knife, etc., that would be small fields that you cannot put a phantom into. So the dose is determined then, and I believe I give you the equation here. The ionization chamber is basically one of the important things, and it's a reference chamber, and I'll define that. The definition for reference chambers in TG-51, the addendum. There are, the ionization chamber is the basic instrumentation for TG-51 TRS 398. And really, we need to do this with reference class chambers. And the definition, as I said, is given in the addendum. There are precautions with small fields, no matter what instrument you use, but I'm not here to talk about small fields this time, so you're going to have to either ask me questions on that later or something else. We'll get to it. So, figuring out the dose for TG-51. The formula that is used is given here. And if you notice the formula before that, it was just M, N sub DW, and KQ. Well, that M is, there's a lot of stuff buried into it. And what is M raw? That's the raw measurements that you make. The P electric, that's electrometer, your calibration factor, coefficient for the electrometer. Temperature, pressure, polarity, and recombination. So the calibration coefficients that you get from the ADCLs are for the N sub DW and for the P electrometer. And those have to be included in there. Temperature pressure correction, everybody's familiar with that. You measure the temperature, measure the pressure, and make a correction for the density of the gas that's within the chamber. Polarity is generally expected to be between 997 and 1003. Now that's modified a little bit, and I'll get to it when I talk about the addendum, but it's not modified greatly. P recombination, of course, is a recombination that you get with the ion chambers. So medical physics 41, that's the addendum again, and reference class ion chambers are defined. KQ factors are elaborated on more further, and especially for new chambers. Percent depth dose at 10 is used for KQ, and the electrometer needs calibration. All electrometers, of course, that we have require a warm-up period. So don't just expect to turn your electrometer on and start taking measurements. Give it a warm-up period, and generally if you're setting things up for your yearly measurements, you'll find that as you set it up and then go to this and go to that, turn the electrometer on first. By the time you get back ready to use it, it'll be warmed up. So some of the addendum clarified some items that were in TG-51. One of the things is the use of a 1 millimeter lead foil led to anecdotal evidence that it's not always removed. So some folks forgot to remove the 1 millimeter lead. And so the addendum recommends that no lead foil be used anymore. So if you're using a lead foil, basically the addendum changed that and you don't have to use the lead foil anymore. This leads to a 0.2% error at the most. So don't worry about that 0.2%, basically. You put it in your uncertainty budget if you wish. The non-water phantoms for yearly calibration are not allowed. That's for yearly calibration. Obviously, when you do your calibration on each year in the water phantom, you would then do a measurement in, say, virtual water or some kind of solid water type of measurement, and then that would be monthly checks that you would do. And that's okay, but it's a calibration for the year, and non-water phantoms is not allowed. You need to uncertainty to it. It's derived for dosimetry and radiotherapy. Table 2 of the addendum outlines this very much, so I suggest very strongly you look at Table 2. I will give you some points of uncertainty, but it's more detailed in the addendum on Table 2. Ion chambers operate generally in a near saturation or saturation region, and I'll show you what that is if you don't know. When a chamber is below saturation, some of the charges in the chamber are lost by recombination, and this defines the saturation region. This is a Q-sat, charge versus voltage, and there's a near saturation period there where it's just sort of coming up to saturation, and then the saturation which is flat across the whole voltage. This is why you measure at 300 and 150 for recombination, because both of those should be in the saturation region. 100 done in Europe can sometimes, for some chambers, get into the near saturation region. So you have to be careful of that. You should know what this curve looks like for your ion chamber. So ion chambers, hopefully this is all review. We have an insulator between the guard and the collector and the thimble area. The thimble is the ground. The collecting electrode and the guard should extend somewhat into the air region. So now if ionization has occurred, this would be like an atom of air, irradiates it, and ionization would occur, and they would separate. However, if there's no electric field, they would come back together, and you would be back with collecting no charge necessarily. You apply electric field, and this is by the voltage that you put on it, say 300 volts, irradiate, and the ions separate, and then they are collected because they go according to the electric field. And this is how it goes up the curve with the applied voltage, staying in the saturation region, which you want. And of course, you go beyond that, it starts heading towards breakdown. And I have an equation here, which I'm going to skip through, not worry about. It basically tells you the density of the air and the measurement in air. So when you have ion chambers, there's an ion collection efficiency. That's basically a measurement of the recombination effect. That's the charge collected versus charge produced. There's a difference because of recombination of positive and negative ions in the gas, and the desired result is to have saturation. Depends on the bias voltage. There are three mechanisms for recombination. General recombination, where opposite charges from different tracks collide and recombine, and initial recombination, that's opposite charges from the same tracks collide and recombine, and ionic diffusion loss, charges diffuse against the electric field. You say, well, what am I measuring? Generally, what you're measuring is general recombination, where the opposite charges from different tracks collide and recombine. The other two are minor in comparison. So this would be the idea. The I stands for initial, as they're on the same track, they would recombine. General, where they're different tracks, and they would recombine. And then diffuse, where they're diffuse against the electric field. So basically, that's the way it goes, how the recombination would be. Now, back to the addendum. A reference chamber is defined by these things. The chamber would settle in and have less than a 0.5% change in reading from the beam on to stabilization. In other words, you turn it on and take a couple of readings. If the readings don't stay within 0.5%, keep taking readings is what it amounts to. And obviously the reading should turn around. The P leakage should be less than 0.1% of the chamber reading. Generally, you can measure the leakage, but it doesn't affect your reading because it's so minor in comparison. P-pole, the polarity, less than 0.4%. Notice it's 0.4% in the addendum. So it's between 996 to 1004. I mentioned previously that it was from 1003. The addendum has changed it, giving you an extra area for the polarity. Unless 0.5% maximum variation in p-pole with the energy. That's across a total range if you're measuring different Linux, 6 MV, 10 MV, whatever. Then the recombination. There are two parts that the addendum talks about. And basically, the general recombination is linear with the dose per pulse. And that's a measurement, different dose per pulses. If you're using 100 monitor units up to 600 monitor units, the recombination for the general recombination should be the same. Initial recombination is less than 0.002 at 300 volts. That correction, all this follows the Bogue theory for chamber dimensions, and basically looking for differences of 0.1%. So the stability of the chamber, this is a reference chamber, must exhibit less than 0.3% change in calibration coefficient over a typical recalibration period of 2 years. In other words, unless something goes wrong with your chamber, it should be within 0.3% of your prior calibration 2 years ago. And this is always a good check. And at the ADCLs, this is about what we look at. Certainly 0.5%, anything more than that says we have to redo it at an ADCL. So let's look at some chamber classifications. And this is from the addendum. Again, they classify different chambers, farmer type chambers. I've given an example of 2 of them there. Scanning chambers, these are the smaller volume chambers by like 0.125 cubic centimeter. Micro chambers, and there's a number of them listed here. Chamber volumes, generally for farmers, about 0.6 cc. Scanning chambers used for beam commissioning, and also some measurements, XRAD and A1SL, for example, volume 0.125. Volumes generally are about 0.1 cc. Micro chambers are for small field dosimetry, but some of them could be used as you need them, and the volume there is less than 0.02 cc. So the majority of chambers meeting reference class are basically 0.6 cc farmer chambers. A150 chambers, that's made of the A150 as opposed to C552, they're explicitly excluded because they have they are hygroscopic. Basically, they will change their calibration with humidity, like in the summer versus the winter. There are 5 scanning chambers that are valid, that can be used as reference class, and the addendum says no micro chambers. The exception might be an A26 from Standard Imaging, because that was developed after and found out the problems with microchambers and were corrected with the A26. So in the long term, just needs to meet the criteria after a 2-year period. It probably does by this time, but it's still not classified as a reference chamber. No parallel plate chambers are included. Polarity. Most chambers do not exhibit polarity differences. As a matter of fact, if you have a chamber that didn't in the past and you see some problem with it, something's gone wrong. You might have dust, you might have problems in somewhere along the chamber. Check it out. Maybe you have to get it changed, looked at by the manufacturer, whatever. But anyway, the polarity is collecting negative charge with plus 300 volts, and depends on the electrometer if it's a plus or a minus there, and then collecting positive charge with negative. In other words, positive and negative charges. If there's a significant difference, the chamber may have a problem, as I mentioned. So these are some polarity correction factors for the different 3 types of chambers that we have. Reference chambers, generally 0.997 to 1003. Again, I mentioned at the addendum, you can have an extra 0.996 to 1.003. So if we look at the reference chambers, meaning 0.6 cc farmers, you notice all of the, look at the column that says mean, and you notice they all lie within the reference given there. If we look, that's to show you. The scanning chambers, you notice there's just one that's listed here, and that is 1.003, and so it definitely falls within for the polarity. Now, if we look at the micro chambers, these are the ones that are in the box, and you'll notice that some of them are bigger than this range. For example, this one, the X-ray in A16 is 10028, which would fall within the 1003. However, if you look at the intermediate one number that we're doing, there was one that came out to 10035. And so these are, when they're this kind of a chamber, the polarity would be not acceptable. However, with the addendum, this is acceptable. The one below that, that is the 10058 and 10006, that would not be acceptable. So you have to check your micro chambers if you're trying to do polarity on that. The volume of the chamber determines the size of the signal, and the volume obviously is determined by the guard. You want a fully guarded chamber where the guard extends into the air volume of the chamber. Some of the old chambers are partially or minimally guarded, and basically the whole question here is how much does the guard extend into the volume? Look at the manufacturer's website and they'll tell you what the chamber is like. The addendum items, reference class ion chambers, KQ factors for new chambers, revised KQ for old chambers. So I actually use all your KQ factors in the addendum, not in TG-51. One exception I'll talk about in a minute. And percent depth dose at 10 is used for KQ. No lead foil, and use equation 15 in TG-51. Generally, it's a 0.2% error if you ignore the lead foil. Use small volume chambers and relative dosimetry. The exception, again, you have to decide this is maybe the A26. Non-water phantoms, nope. Only water for dosimetry, especially when you're doing your yearly. Checking monthly checks, that's fine. And you want to develop an uncertainty budget. Now this is new for a lot of physicists. I will show you what uncertainty is about here, but look at table 2 again of the addendum. So for KQ, for our chambers listed in both the addendum and the original TG-51, use the KQ values in the addendum. They're modified and better values. Chambers that are not listed, in other words, use all of the KQ factors that are given in the addendum. If they're not listed in the original or in the addendum, look at the recommendations in paragraph 11 of TG-51 and follow them. I highlighted the areas here, but the wall material and responsibility of the user to find out what it is. Uncertainty. I wanted to go through this a little bit for you so you understand it, but again, look at table 2 to give it a full feel for this. Type A measurements are standard deviations of the measurements, like your measurements that you make with your electrometer and ion chamber. Type B are scientific judgments. They're from reference books, manufacturer statements, etc. You have to calculate what the type B is. It's an uncertainty in your experiment. It's not an error. The old way was talking about this was an error. If it's an error these days, you correct it. That means you've done something wrong. So you correct it. Uncertainty is the present term to be used when you calculate your total uncertainty of your experimental setup. So there's definition of terms very quickly. Standard uncertainty, that's expected range. Expanded uncertainty, that's a coverage factor, generally factor of 2. That corresponds to 95% of your readings will be within that area. And it's designated by 2, so K equals 2. Uncertainties in percent are combined like in square, and then take the square root, and it's done in tabular form generally. Calculations done at K equals 1, and then generally you multiply by 2 when you're finished. And a mathematical relationship, if you know it, you can propagate the uncertainties by partial differentiation. That could be for temperature pressure, for example. This is just an example of ADCL to the clinic chamber transfer. This is uncertainty of your chamber when it comes. And we list the charge, the timing, air density, and so on. Each of these listed in type A, the measurements that we made, or the type B values. And then the quadratic sum is that square of all the type A's and all the type B's, type A and B, quadratic sum, squaring and taking the square root. And so the then we add at the bottom the electrometer readout and transfer calibration. The electrometer readout because this is just the chambers up to that point. And then basically we find a type 1, the K equals 1 value, and then multiply by 2 for K equals 2. 95% of your values would lie within 1.36%. If you notice on your added to your chamber, it's usually 1.4%. So calibrated of the chamber every 2 years in an ADCL. Redundancy of chambers for QA purposes. In other words, make sure that your chamber is maintaining the QA, and recent discussions on 2-year calibration and ionization chamber. So you're wondering, how do we go about doing this? Well, the present situation, TG-51 says, equipment is to allow for 2 independent checks of a secondary standard ion chamber. Check sources, independent dosimetry, a cobalt unit, etc. This is section 5 of TG-51. This is usually interpreted as strontium-90 check source. That's IEC 60731. Basically, that's for manufacturers. It's not for clinical users. Now, we need to consider the TG-51 Addendum. And the 51 Addendum says the chamber performance should be verified on a regular basis. That's 5.B.4 of the Addendum. Between calibrations at an ADCL, the long-term stability of the reference chamber should be monitored by the user. This is a quote from the Addendum. The method recommended is a regular comparison with other reference class ionization chambers in a LINAC beam. At least 3 chambers are required to make such a comparison method robust, although not necessarily to have all 3 calibrated at an ADCL. In other words, you should be intercomparing 3 of your chambers, and you can do it however you want. I'll have Autumn Walter, my colleague here, talk about it, and she will give you the experiments that have been done on this. So here are the methods from the Addendum. Use a cobalt source. Very few people have a cobalt source available. So reuse redundancy, 3 chambers in a LINAC beam, or use a strontium-90 check source. Chamber should remain within plus or minus 0.5%. Redundancy is a better method than the strontium check source, and it's a replacement technique, but there you have setup errors, changes with time, or do all 3 at once. Autumn Walter will talk about the constancy phantom coming up. So the recommendation is from the Addendum says use them all at once. And in addition, the LINAC basically that you're doing, you're checking the output of the LINAC at the same time with your reference chamber in the center. So just a comparison quickly, the probability of not finding a problem if 3 chambers are compared, 1 chance in 4 million. That's from Rosenfeld, and yet the reference is given there. Using a strontium-90 source is 1 chance in 100, not a million. So the author of the paper, Physica Medica, is Autumn Walter, and I turn it over to her now.
Thank you, Larry. So like he mentioned, I'll be talking about some different methods for evaluating ionization chamber stability that we performed at the UW-MRC. So this is just a brief outline of what I'll be talking about. A lot of the summary will be the same as what Larry just mentioned. Go through some of our methods that we did at the UW-MRC, comparing Cobalt-60, Strontium-90, and the linear accelerator, and then highlight some results and conclusions. I'd just like to disclose this work has previously been published in Physica Medica, as mentioned. As mentioned, a lot of regulatory bodies like the NRC and the AAPM recommend that independent quality assurance checks be performed for ionization chambers in between calibration cycles. Cobalt-60 was originally recommended by the AAPM, but as mentioned, this has shifted to other uses such as the linear accelerator beam, which the chambers are used in. Cobalt-60 radiators are being phased out of clinics due to some regulation issues and aren't common in the United States anymore. A number of other methods that have been recommended include sequential measurements in beta-emitting check sources like strontium-90, the cross-calibration of ionization chambers at the clinic, as well as these redundant chamber checks in linear accelerator beams. The IEC originally recommended the use of strontium-90, but as Larry mentioned, these were recommended for manufacturer purposes. This check source, which is shown on the right, is enclosed in a lead shielding casing and has an insert for a chamber at the top. There are a number of advantages to using these sources in the clinic, as they're long-lived and generally show independence from environmental factors like temperature, pressure, and humidity. They can also be easily transported from room to room within a clinic. However, there has been a lot more observed variability when using strontium-90 due to positioning uncertainties as well as decay of the sources. The check source housing also limits the chamber compatibility, as the stem of the chamber must be thin enough to fit within the insert on the top of the check source, and requires specific regulations in training and licensing within a clinic. In 1984, these redundant chamber checks and external beams were recommended by Rosenfeld and Jett. This includes the comparison of 2 or more chambers in an external field. These methods can be incredibly efficient as simultaneous measurements are taken, and the likelihood of detecting a faulty chamber increases dramatically. For example, if you're measuring a single chamber in a linear accelerator beam, you might find that it's without the set plus or minus 0.5% threshold, indicating that there may be an issue with your chamber, causing a user to send their chamber back to the manufacturer or to get it recalibrated at an ADCL. If you're comparing 2 or more chambers with the same setup, you might find that all of the points in that measurement are trending, possibly indicating a positioning error or a problem with your machine or other equipment being used, like your electrometer. This method does require multiple electrometer inputs and chambers to be used, as the same electrometer input should be used for each measurement, and they should be performed simultaneously to give the best results, and different regulations are required for linear accelerators. However, in the clinical setting, these regulations are being followed for linear accelerators. So the overall goal of this work was to evaluate the use of strontium-90 and these external beam qualities, such as Cobalt-60 and linear accelerators, in terms of precision and efficiency for performing single chamber and redundant chamber checks. The Cobalt-60 results were made from data at the UW ADCL for 3 ionization chambers: the NEL-2571, PTW-N30001G, and XRAD and A12 farmer type chambers. Inner measurements taken at the irradiator at the UW ADCL were compared over a 10-year period. All measurements were made with the same MAX 4000 electrometer, and the readings for the N30001G and 2571 were compared to the NIST-calibrated A12 response and tracked over the 10 years at the UW ADCL. 3 chambers were used for the strontium-90 methods: the Wellhofer IC69, XRAD and A28, and XRAD and A12 firmer chambers. They were evaluated in the strontium-90 check source shown below. The IC69 and A28, in the middle and right respectively, were inserted such that the tip of the chamber was resting on the bottom of the check source well. The A12, however, was not inserted fully into the check source. This is because the stem of the chamber was thicker than the hole on the top of the check source, and only the thimble could be inserted into the volume of the chamber, of the well chamber of the check source. 2 initial tests were performed to characterize the check source prior to use. This first check was the response profiles taken with the A28 chamber. This chamber was used as it has a small volume and is traditionally used for scanning measurements in linear accelerator beams. To start, the tip of the chamber was placed at the bottom of the check source cavity and moved in 1 millimeter increments from the bottom of the cavity. 3 15-second charge readings were taken at each position to determine the hot spot of the source. Additionally, the rotational dependence of the chambers was evaluated in the check source. The line on the stem of the chamber was aligned to the line on the front of the check source, and the chamber was denoted as the 0 position at that position. 15-second charge readings were taken at each location, inserting the chamber before each measurement was taken, as recommended by the manufacturer. The chamber was rotated in 90-degree increments about the 0-degree position, and the response at each location was normalized to the 0-degree position. For the measurements for monitoring the stability of the chambers, each chamber had a 300-volt bias applied, and at least 10 15-second charge measurements per chamber were taken, with reinserting the chamber before each measurement was taken per the manufacturer. A total of 11 measurement trials were performed with at least 3 days in between measurements to evaluate the stability over time. For the linear accelerator measurements, the standard imaging IonQA constancy check phantom was used in a Varian 21EX Clinac linear accelerator. This phantom is a 30 cm by 30 cm by 3 cm slab of virtual water with holes milled out to hold custom plugs for the ionization chambers. These plugs are machined such that the chamber volume is placed within the plug, and then these plugs can be inserted into the phantom, holding the active volume of the chamber along the central axis of the beam. The beam can be aligned to the crosshairs on the phantom. For this work, the phantom was placed between two 5 cm thick slabs of virtual water. The linear accelerator measurements were made using a supermax electrometer with 2 electrometer inputs and a max 4000 electrometer with 1 input. An SSD of 100 cm was used, and a field size of 20 cm by 20 cm was used. This larger field was chosen to ensure that the chambers were all within the flattest portion of the field and to eliminate any effects from penumbra. Similar results were also seen for 10 cm by 10 cm, but there was some more variability on the chambers at the outer edge. A 6 MV beam with a 600 monitor unit per minute dose rate was used, and a 300 volt bias was once again applied to take charge readings for 10 100 MU irradiations. 10 irradiations were chosen to keep the measurements consistent between the strontium-90 and linear accelerator methods to have an accurate timing comparison. The chambers for these methods were measured on the same day as the strontium-90 methods. Both sequential single-chamber measurements and simultaneous measurements were made with this phantom. The sequential measurements were made by placing each chamber at the center of the phantom, and the left and right positions within the phantom were filled with a blank virtual water plug. Each chamber was read and its respective electrometer input, and these measurements were tracked over time. Additionally, all 3 chambers were placed within the phantom, and the simultaneous measurements were taken with all chambers plugged into their electrometer inputs. For each measurement, the charge readings were corrected for the electrometer correction as well as the temperature and pressure correction. In addition, the strontium-90 and cobalt-60 measurements were corrected for the decay of the source. The charge ratios for each method were calculated by taking the ratio of the corrected charge reading for a chamber X over the corrected charge reading for the chamber X prime. For the case of the cobalt-60 measurements, the X prime value was the A12 value. These ratios, as well as the individual chamber readings for each method for the strontium-90 and linear accelerator, were normalized to the initial baseline measurement, which will be denoted as B. Shown here is the cobalt-60 data tracked over time from the UW ADCL. You can see no clear trend is observed with either chamber with respect to the A12. The percent differences all lie within plus or minus 0.5% from the initial baseline value as shown here. Shown here is the response profile for the strontium-90 scanning profile measurements. You can see the hotspot lies around 0.5 to 0.7 cm from the bottom of the chamber well. Additionally, here is the rotational dependence of the chambers within the source. As you can see, the IC69 exhibits a very small rotational dependence within the check source well, but the A12 and A28 vary by up to 1% different, indicating that it is incredibly important to input these sources in the check source in the same way for each measurement taken. Shown here are individual charge readings for the A12 and A28 ionization chambers in strontium-90. As you can see, there's a clear trend in the data, especially with that final data point outside of the 0.5% threshold. One might think that there's a problem with their chamber if only looking at one of these checks. Additionally, the A12 charge readings have a large amount of variation, with standard deviations of over 1% in some cases. When comparing the charge ratios, however, you can see that this final data point falls within the 0.5% threshold. However, there are still ratios outside of that threshold set, which could potentially lead someone to believe their chamber is misbehaving. However, due to the spread of the data, it's very difficult to tell if there is in fact a problem with the chamber or if it is just noise of the measurements from these positional uncertainties within the strontium-90. A similar trend is shown when comparing the A12 and the IC69 chamber. Once again, that final data point of the IC69 is well outside of the threshold set of plus or minus 0.5%, while all the other data points have a very small uncertainty and fall within this threshold. When comparing these ratios again, you see there are still a few points outside of that threshold, but once again, the A12 was so noisy, so it's very difficult to tell. And that final data point, where both points seem to be trending, fall well within that threshold. Finally, just comparing the A28 and IC69 chambers with a much lower uncertainty, that final data point is outside of the threshold again, as observed from the other two comparisons. However, when taking the ratios, We find that all of these values fall well within the threshold, indicating that there might be an issue with the noise of the measurements for the A12 chamber and could lead to problems with detecting faulty chambers, as well as wasting clinicians' time when determining these. So to summarize the strontium-90 results, the hot spot of the source sits approximately 0.5 cm from the bottom of the source well, which could be problematic when measuring the A12 chamber, as this volume of the chamber sits well outside of that region. Overall, there is a 1% rotational dependence for a given chamber when rotated within the check source, which can be seen for the A12 and A28 chambers. The A12 exhibited the largest amount of variation, with around a 1% standard deviations for a single measurement trial, which can lead to more noise in the data and difficulty in detecting faulty chambers when performing stability checks. All individual chamber readings deviated from the baseline reading by a maximum of 1% and was minimized when taking the ratio of the A28 and IC69 chambers. However, it was not seen to be minimized when comparing the A12 to the other two chambers. Overall, the positioning of the chamber within the check source plays a significant role in the overall precision of the strontium-90 check source methods. Now moving on to the linear accelerator measurements. Shown here are the A12 and A28 charge readings for those same days for the linear accelerator methods. As you can see, the precision of these values is a lot smaller than the precision of the strontium-90 results, but that final data point is once again trending upward. When comparing the ratios, one will find that they all fall within the set threshold. The results here for the linear accelerator measurements show a completely different story than the strontium-90 results, as there is a lot more precision and all fall within plus or minus 0.3% of the baseline value, indicating that the positioning uncertainties for the strontium-90 play the largest influence into the results from that method. Similarly, for the A12 and IC69 comparison, you see that the IC69 final data point falls about 0.75% higher than the initial baseline value. One might think that their IC69 chamber is perhaps misbehaving and should be reevaluated. However, when comparing the ratios once again, all of these values fall within that plus or minus 0.5% threshold. One might think that their chamber is having an issue just because of that data point, but these values for the ratios show a much different story. There could have been an issue with perhaps the positioning of the phantom within the beam for those measurements, as well as perhaps an issue with the electrometer on that day, as the MAX 4000 electrometer and Supermax electrometer were used for the same measurements as the strontium-90 results. Finally, just for completion, the A28 and IC69 values are shown here, showing that same trend, and when they're compared as ratios, they show a very similar trend as the other two comparisons. Overall, all of the chambers had a standard deviations of individual measurement day of less than 0.2% for a given trial, and the individual chamber readings were all within the plus or minus 0.5% threshold set, with the exception of that final IC69 point. These results show a different story when compared to the strontium-90 results, mostly due to the noise in that data. The final measurement point exhibits the same trend for the sequential chamber measurements, and this trend is eliminated when comparing the ratios from the simultaneous measurements. So in conclusion, the external beam measurements, whether using Cobalt 60 or the linear accelerator, provide a much more precise method for monitoring the ionization chamber stability when compared to strontium-90. Overall, regardless of which method you use, methods should be reproducible to have the limited uncertainty possible within a measurement trial. Comparing ratios, whether with true redundant checks from simultaneous measurements or in sequential measurements for single chambers, provide a more robust method for tracking chambers over time. This can cause a savings of time from reevaluating chambers if you believe they're being faulty when comparing the two ratios, as well as allow you to save money from trying to send your chamber, for example, to the manufacturer for repairs or to the ADCL for recalibration of your chamber when it's not necessary. Overall, the use of the constancy check phantom for simultaneous measurements provided a much more efficient method for performing stability checks, as the measurement of the three chambers at one time took a total of 15 minutes with setup and tear down time when compared to 38 minutes for the strontium-90 methods. I'd finally just like to thank the UW ADCL customers whose continued patronage supports ongoing research at the UW MRC, and thank you to the staff and students at the UW MRC for their assistance with this work. We'll be happy to take questions.
Thank you for joining our presentation. It looks like no questions have come through, so we thank you so much for listening. Please don't hesitate to reach out to us at standardimaging.com with any questions. Our team is happy to help. Thank you.